Welcome to part 4 of my lecture series on residuals in CFD. This is going to be the final talk in the lecture series, and I'm going to talk about global imbalances and how these are different to the residuals that we've looked at in the past few talks. I'm then going to carry on in this talk to look at a variety of different monitors which you can use to help assess the convergence of your real CFD cases. I'm hoping that by the end of this talk and by the end of the series that you're going to have a newfound confidence in assessing the convergence of your CFD cases and interpreting the results of the residuals and the imbalances and the monitors so you can make a confident assessment of the convergence of your CFD cases. Right, I'm really excited to get into this talk. Let's get into it. So I'm going to start things off with a quick recap of what we talked about in the previous parts of this lecture series. Recall from part 1 that the simple example case we were looking at is 1D heat conduction in a bar, and we used this example to understand the concept of residuals and scaling. Now for this example of 1D heat conduction in a bar, we've got a hot end of the bar which is held at a fixed temperature, and then we've got a cold end of the bar at the right end which is held at another fixed temperature. And between those two extremes we've divided our mesh into 4 cells. And of course, heat will flow from the left end of the bar from the hot surface to the right end of the bar at the cold surface. And for the example problem, we've got no sources of heat in the bar, and so for 1D conduction, the resulting solution, the temperature profile, will be linear between those two ends of the bar. And rather than solve this problem by hand, we formulated this problem as a matrix equation by applying conservation of energy to each of those cells in the bar. And this resulted in a matrix equation AT equals B, where T1, T2, T3, and T4 are the temperatures at the centroids of each of the cells in that mesh. And also recall that in general, CFD solvers are iterative. That means that the solution is approached in stages and the solution gets closer and closer to the final solution as we converge. And while we're converging the solution for this example problem, the temperature profile will of course not be linear because we haven't quite reached the final solution yet. And because the temperature profile isn't fully linear, although it is piecewise linear between the centroids in the mesh, if we look, for example, at the sections of the temperature profile that you can see there in the graph, and we look at the temperature gradient gives us the heat flux across the faces of the cell using Fourier's law. And we can quite clearly see that for this example, if we look at the third cell in the mesh, the temperature gradient across the left face of the cell is much steeper than the temperature gradient across the right face of the cell. And this means that there's the heat flux across the left face of the cell is not equal to the heat flux across the right face of the cell. Because we have no sources of heat in the bar, this means that for this particular cell, energy isn't being conserved, and we're losing some of that energy somewhere. And the residual gives us that missing energy, or the energy imbalance for a particular cell in the mesh. And what we can do to calculate the residual for every cell in the mesh is to take that solution, the temperature vector, T1, T2, T3, and T4, and substitute that back into the equation AT minus B after we've made an attempt and we've gotten it a solution T, which is not the exact solution. We substitute that in, and that allows us to calculate the residual vector, which gives us the energy imbalance for every cell in the mesh. And of course, as the solution converges and the temperature vector gets closer to the final solution, the residual vector reduces towards 0, and that means the energy imbalance is reducing towards 0, and we're getting closer to convergence. And then what we did in part 2 and part 3 is we took that idea of the residual being the local energy imbalance in every cell in the mesh, and we extended this to look at scaled residuals and normalized mass imbalances and why we needed to do that. And the reason that this process of scaling is needed, of course, is if you look at this example you can see here on the slide, if you look at the second cell in the mesh, you've got 49.1 watts coming in across the left face and 49.5 watts going out across the right face. And so there's an imbalance of 0.4 watts. And so for that particular cell, the residual, the unscaled residual, is 0.4 watts in the second cell in the mesh. And we would normally scale that residual so that the 0.4 watts is expressed as a percentage of the total energy flux going through the bar, and that will give us an indication of how close we are to convergence. And the takeaway point from that that's going to be applicable to this lecture here is that the scaled or normalized residual, depending on how we calculate it, is representative of the local imbalance in a particular cell in the mesh. And that's really what I want you to be thinking about here, is that this residual, when it's scaled, we're talking about the imbalance in a particular cell in the mesh. And that's why every cell in the mesh has its own residual, and we get a representative value which we plot on the graph. But the first focus of today's talk is we're going to shift away from that idea of a local imbalance in a particular cell, and we're going to now move on to look at the global imbalance for the entire solution. And to illustrate the global imbalance and to help you understand what it is, we're going to take the same example of the 1D heat conduction in the bar, and of course for the converged final solution, the heat flux should be constant along the bar. So this is, of course, the gradient of that straight line for the temperature profile is constant. It's a constant gradient, and so the heat flux should be constant through the bar. So the heat flux across the left face of one cell should equal the heat flux across the right face of that particular cell, and so on across the mesh, because we've got a 1D problem. Now, what I want you to think about is that because the cells are connected, this has an effect on the cells that are downstream of the current cell. So if you think of that second cell in the mesh, the second cell from the left, this cell has got 49.1 watts of heat coming across the left face. And now there's an imbalance of 0.4 watts in that cell. So what that means is that the heat that goes out of the right face of the cell is 49.5 watts. But now there's an error in that's the residual, but that error is now propagated forward into the next cell in the mesh. Because for that third cell has got 49.5 watts coming into it, not 49.1. And as a result, the heat flux out of the right face of the third cell is 49.8 watts. So you can see that locally, the second cell has an imbalance of 0.4 watts, and the third cell has an imbalance of 0.3 watts. But the net effect is now become 0.7 watts because the error is accumulating as you're moving along the cells in the mesh. And this is the key idea for the global imbalance. Because faces are linked, it means the error can be propagated from one cell to the next. And what that means is that if we actually plot the heat flux along the bar, of course the final converged solution should just be a flat horizontal line where the heat flux across one face becomes the heat flux across the next. What we find is that for this particular example, that error is propagated forward. And so we see, if we compare the left end of the entire bar with the right end of the entire bar, so the entire domain, we can see that the net error, or the net imbalance in the heat flux, is actually much larger than the local imbalance across a particular cell. That's because that heat flux error is being propagated forward. And this difference between the heat input at the left boundary and the heat output at the right boundary is called the global imbalance. So global because it's the entire domain, rather than the residual, which was looking at the local imbalance for a particular cell. And this is what I wanted to show you on this second graph here, and it's a way you can think about it, is that the difference between those 2 points in the heat flux graph, that's going to be the local imbalance for a particular cell, but the red lines there, which show the difference between the left boundary and the right boundary, is the global imbalance. And even though we've got a mesh of cells and we want to solve our solution, our continuous flow field on our mesh, so we want a continuous solution throughout the domain, for many problems, actually, the global imbalance is much more important, because often we're propagating heat or a force of some kind from one part of a domain through a fluid to another part of the domain. And if we're calculating, for example, the forces on a surface, so if you're calculating lift and drag coefficients on an aerofoil, for example, or the heat transfer coefficient from a hot surface, these are the forces and the heat fluxes that are recognized on the boundary of the domain rather than in the middle of the domain. Because remember, really what we're doing in CFD is we start with an overall geometry and then we arbitrarily slice that geometry up into little cells so that we can capture everything throughout the domain. But for many quantities, what we actually care about is what happens on the boundaries. And so we need to have a metric that measures the global imbalance as well as the local imbalance. So the residual is going to give us a measure of that local imbalance, but what we actually want is the global imbalance. And another way you can think of this, which is helpful to me as well, is consider the same example where we've got that 1D bar between a hot temperature at the left end and a cold temperature at the right end. But now instead of using 4 cells, imagine that we sliced this up into loads and loads of little cells. And if we did that same plot of the heat flux along the bar, which should be constant, we can see that in this case, because the cells are really small, actually the local imbalance between each of those cells, in this particular case, at this iteration, the local imbalance actually looks quite small because the cells are very close together. But because we've got a large number of cells in this case and each one has its own local imbalance, by the time we get to the other end of the surface, the cold surface in this case, the global imbalance between the left end of the bar and the right end of the bar is actually quite large. So it's important to look at the global imbalance alongside the residuals, so at the same time. And before I move on, I just want to make the very key point here that just because I've shown this example with a fine mesh where the local imbalance is a lot smaller than the global imbalance, just does not mean that if you refine your mesh, for example, that your local imbalance will get smaller and your global imbalance will get larger. Definitely don't make that misconception. This is just an example here to show you that there is definitely a difference between a local imbalance or a residual and the global imbalance. And it's important that we look at both of them because an error can be propagated forward through the mesh. Now, thinking about this idea of global imbalances, so we're now just looking at the left end of the bar and the right end of the bar, and we don't really care about what happens in the middle for the moment. If you consider the case on the left where we've got 15 watts of heat coming in the left end of the bar, and then at the right end of the bar, we've only got 14.8 watts going out. So the global imbalance in this case is 0.2 watts. We've lost 0.2 watts somewhere along the bar due to our iterative solution process. And if you compare that to the case on the right, where we've got 1 watt of heat coming in the left end of the bar and 0.8 watts going out the right end of the bar, you can also see that for this case, there's a global imbalance of 0.2 watts. But once again, following the same reasoning that we've used for the residuals and the mass imbalance, it's the percentage of the global imbalance relative to that total flux of heat going through the bar that's important. In the case on the left, we've only lost 1.3% of the heat. So only 1.3% of the heat is not being realized because of our iterative solution. Whereas in the case on the right, we're actually losing 20%. We've got a 20% error in the total heat coming into our domain and going out of our domain. So in the same way as the residuals and the imbalance, it's important that we express the global imbalance relative to the flux of the quantity going through the domain. So I'm taking that same example again. And this is why many CFD codes like ANSYS CFX, for example, when the global imbalance is available, it's often expressed as a percentage. And the way you'd calculate that for the energy equation, of course, would be the total energy in minus the total energy out, and then divided by the total energy in. And that will give you a percentage imbalance. And this also helps for us as CFD users to assess the convergence of our CFD codes. It's nice to know, for example, if we're only losing 0.1% of our total energy in our CFD solution, that would probably give us a bit of confidence that our solution is globally balanced. Whereas if we're losing 10% of our energy, that might indicate that we have to do something to our CFD solution because we're losing a lot of the heat. Now, so far, I've only looked at a simple example, as before, of 1D heat conduction in a bar. We've got heat coming in the left end and heat going out the right end. But what do we do for real CFD cases that are more complicated, that have perhaps got many, many different boundaries? So if you consider, for example, a backward-facing step flow, this is quite a nice example of a 2D flow that again is very simple and straightforward. You have one inlet at the left end, one outlet at the right end, and then a series of walls there. And of course, real CFD cases can be in 3D, and you can have many walls and sections of surfaces and things. And if we now start to think about these global imbalances and how we might calculate them for real domains, a mass imbalance would be very straightforward and easy to calculate. What we would do is just calculate the mass flow rate over the left boundary of the domain, and then the mass flow rate over the right boundary of the domain, and the difference between them would give us our global mass imbalance. And mathematically, we would do this using an integral. Of course, the CFD codes often have discrete forms of these integrals, which you can use readily in your post-processors to calculate mass flow rates over inlets and outlets. And of course, if you have multiple inlets and multiple outlets, you'd need to work out the mass flow rate across all of your inlets and all of your outlets and subtract them to work out what your global imbalance would be. Now, for energy you have to do a little bit more thinking than for mass, because of course mass can only leave the domain through inlets and outlets. It can't pass through walls because we have the no penetration condition on velocity. But for energy imbalances, you need to think a bit more about your surfaces and what you have. You would want to know the heat being advected into your domain across your inlets, also across your outlets, and then also through your walls that are not adiabatic. You also can be losing or gaining heat through those walls as well. Now, just from the discussion that I've presented so far, this can look like a bit of a daunting task because you're having to do integrals of mass flow rates and heat fluxes across lots of boundaries, and coding up an integral like that might be quite difficult for you. But what you'll find, most CFD codes already have the capability to do these integrals for you, and so actually it's often quite easy to set up the global imbalances yourself manually. For example, if you have one inlet and one outlet, often CFD codes as a monitor. When you're setting up a solution, you can monitor the mass flow rate across a particular surface. Then what you could do is monitor the mass flow rate across all of your surfaces, and then calculate the summation, and that would give you a global mass imbalance. And you could do the same for your energy as well. And if you express that as a percentage, that will give you the percentage imbalance. And I find it quite useful at this stage just to take a step back and think about what it is we're actually doing when we're assessing a CFD solution using global imbalances and residuals. What you can see even from this simple diagram, that the global imbalance is really being calculated at the boundaries of the domain. So when we're thinking about a CFD domain and we do a global imbalance, we only care about what's happening on the borders or the boundaries, and we don't actually care about what's happening inside. Whereas with a residual, what we're doing is we're looking at the local imbalances for all of those cells or all of the pieces inside the domain, and then we're taking a representative value using the L1 norm, the L2 or the L infinity norm, for example, to get a kind of average of how the local imbalance is varying through all of the pieces of that mesh within the boundaries. So that's a nice way of thinking about it. You've got the global imbalance, which is looking at the boundaries, and then the residuals, which are looking at the inside part of what's happening in the mesh. And the next level of abstraction to think about is that what's actually happening here when you're doing a global imbalance is, because you're only looking at the boundaries and the edges, what's actually happening is you're treating your entire CFD domain as a control volume. And this is quite a nice conceptual step that I think if you now go ahead and just think about what your CFD domain is perhaps that you're solving, or what particular case you're solving, and think of your entire fluid domain as a solid object or as one single object with surfaces on it. And what the global imbalance is doing is looking at what's the flux of mass and heat and things over the surfaces of that global object, where you're not really caring about what's happening inside that object. And if you go back to very early stage fluid mechanics that you may have learned, you may remember that this type of control volume analysis is actually what you would have done to do hand calculations of various systems without actually knowing what's going on inside. Well, now we're in CFD and we're looking at the global imbalance. We're actually taking a step back and treating our entire CFD domain as a single control volume. And it's quite a useful thing to do when you look at your own CFD cases, is look at your fluid volumes or your solid volumes and try and think of them as a single continuous object. Now, when we're assessing convergence, what we really should be doing is plotting the residuals and the global imbalances and using them together to help assess convergence. And when we do that, we may have something that looks like the images you can see here on this slide. I've got the residual plot on the left and the global imbalances on the right, and a little image there just to kind of remind you of what it is you're actually doing. When you have that residual plot, actually you're looking at the imbalance in local cells or local pieces of the domain, and of course averaged over the domain in some way. Whereas when we're looking at the global imbalance, we're actually just considering the boundaries or the edges of that domain. And both of these quantities together are useful when assessing convergence. And definitely myself, when I look at these things, I find the global imbalance intuitively easier to understand, because we can all quite easily understand what a global imbalance of 1% actually means. It means that if we have 100 units of the quantity coming in and 99 going out, we're losing 1% of that in our domain. Whereas residuals can sometimes be more difficult to interpret, as it's not clear what 1e to the minus 3 or 1e to the minus 4 actually means. Now, some CFD codes will actually calculate these global imbalances for you automatically. Now, ANSYS CFX is one particular code where when you're monitoring the solution, you can actually just watch the global imbalance. It's already there calculated for you. And so you can get a plot which looks like the plot on the right. But if you use another CFD code, or if you've written your own CFD code and you want to look at the imbalance, then actually what you'll need to do is set up each of the pieces of the monitor yourself. So for example, if you have a channel flow like we've got there with one inlet and one outlet, you'll want to put a monitor for the inlet mass flow rate, a separate monitor for the outlet mass flow rate, and then either within the monitor or yourself calculate the difference between them and divide by the mass flow rate, and you'd have to calculate your global imbalances a bit more manually. And if you plot those, you'll actually sometimes get plots which look something like this. This is an interesting one where if you plotted the mass flow rate coming into this domain of this 1D channel and then the mass flow rate going out, of course what you'll see is that when you get close to the convergence, the mass flow rate going in is almost equal to the negative of the mass flow rate going out at the other end. So implicitly what this plot here is showing is it's a measure of the imbalance. You would have to take the difference between them and divide by about 5, and that would give you the imbalance. Now, what I've started to do here is to look at and mention how you might assess the overall convergence of a CFD case. And overall, over the past 4 talks in this lecture series, we've looked mostly at residuals, and I've just introduced the global imbalance as well as another way of looking at convergence. But actually, what you're probably starting to see is that we're building up an overall picture for how we assess the convergence of our CFD case. We've got the residuals that look locally, we've got the global imbalances which look at the boundaries. What other things can we do? And the reason this is important is that every additional metric that we add to help assess convergence provides a better overall picture. Because if we just go with residuals, we perhaps don't know anything about the global imbalances, whereas if we just look at the global imbalances, we don't really know what's happening with the residuals or the flow field itself. And the real takeaway point from this lecture series is that when you set up metrics and monitors in your CFD case, whether you're setting up a monitor for the mass flow rate or the global imbalance, this often only takes a few minutes during the case setup. But by the end of the case, when you're looking at convergence and you want to see how good your solution is, the more monitors you have, the more information you have, which can help you make that judgment call. So often spending a few minutes of putting lots of additional monitors in when you set up your CFD solution can be really helpful. And there are many different types of monitors that you could use in addition to residuals and imbalances. The most obvious one being point monitors. And point monitors are perhaps some of my one of my favorite metrics to look at when I'm assessing the convergence of a CFD solution, as they give you a direct insight to what the CFD solution is actually looking like in your domain. And what you do with the point monitor is pick some locations in the domain and look at some flow variables and how they vary through the solution process. And many of you will be used to doing this. And you can look at metrics like velocity, pressure, species concentration, mass concentration, for example. And these are really good metrics as well, particularly if you have a steady state case. You expect your point monitor to reach a constant value. And that's an additional metric for assessing convergence, as well as the imbalances and the residuals. And an interesting thing which you might notice if you use point monitors a lot is that the flow field often develops a lot more quickly in some areas than others. And I've just wanted to show this with a simple diagram for you on the slide here, where if you put a point monitor right next to the inlet of your CFD domain, you'll often find that the velocity there converges very quickly. And the reason for this, of course, is that information, or the effect of the boundary, is propagating through the domain from the inlet to the outlet. And so the velocity near the inlet actually tends to converge very quickly. Whereas that same monitor, if you placed it near the outlet, often takes many more iterations to converge. And this is why if you're using point monitors, it's often a good idea to place lots and lots of different point monitors in the domain, so you get an idea of how the solution is changing throughout the domain. And you can also use it to observe features in the flow field. And for this particular case of a backward-facing step flow, if you placed some point monitors right behind the step, for example, you would often find that the velocity and other flow variables at that location can be unsteady, and you'd be able to see that in the point monitors as well. And the reason this is useful is that often this unsteadiness in the flow field that's physically developed, either due to separation or buoyancy or some other effect, is often manifested in the residuals and the global imbalances. So what this is doing, you can see, is it's providing you more information and more of a picture of what's actually going on in your case while you monitor it. So you may look at your residuals and see that your residuals are oscillating or doing something, and you're not really sure why, because residuals on their own don't really tell you anything. It's just an average picture of what's happening within the domain. And that residual may be dominated by some unsteadiness that's physically occurring in the flow field, for example, behind your backward-facing step. And this is one of the reasons why monitors are a great way to support your residuals and your imbalance estimates. And as I've shown you, of course, in the previous two slides, because information or the effect of a boundary propagates through the domain while you're solving, the monitors, it's useful to have lots and lots of different monitors at different locations in the domain. Of course, you can monitor more than one variable. You don't just have to look at velocity. You can look at temperature and pressure at different locations in the domain. And for this example, you can see that I've put some easy monitors in a variety of places. One by the inlet, one by the outlet, quite a few near the wall where I think the separation, the reattachment point may be from that flow that's separating from the corner. And I've put one monitor right there behind the corner as well. And generally monitors are extremely easy to set up because all you really need is the coordinates and the quantity that you want to measure. You can put lots and lots of these monitors everywhere throughout your CFD domain, and they all give you a good idea of what might be happening at that particular location in a domain. Now, of course, a monitor is only a single value and it doesn't fully provide all the information you want. And so if you do see some flow feature that you're not sure about in the monitors, it may be represented in the residuals, you can always open up the post processor and have a look at the flow field itself using a contour plot to have an even closer look. All of these techniques are building up information that you can use to help assess your convergence. And what about maximum and minimum values? These are also extremely easy to set up, and they also help provide sense checks that your results are converging sensibly and you haven't diverged or set up something incorrectly in your case setup, for example. Now, if you have a very simple flow domain with inlets and outlets, and you don't have any heat sources in the domain, for example, you only have boundary values, then you expect the temperature and the flow field solutions to be bounded between extreme values. And that might seem like quite a complicated phrase, but what it physically means, you can understand this if you just have a look at the diagram I've got for you on the slide, where we've got that same backward facing step flow, but now we're going to assume that the flow field coming in is at a temperature of 400 Kelvin and the top wall is heated at say 500 degrees, and what we're doing is we're monitoring the maximum and the minimum temperatures throughout the domain. Now, physically, we can look at this straight away and tell that because there's nothing in our boundaries that's hotter than 500 Kelvin, then we expect our solution within the domain to be bounded somewhere between 400 and 500 Kelvin. And so if we monitor the maximum temperature, for example, and we see the temperature is 550 Kelvin or 300 Kelvin, that gives us a really good indication that either our solution is diverging or maybe that we've set up one of our boundary conditions or our user-defined functions incorrectly. So looking at maximum and minimum values is another way of monitoring what's happening in your solution and checking what's going on. Now, some of you may be looking at a specific quantity when you're calculating your CFD solution. So, for example, if you're solving the flow around an aerofoil or a lifting body, you may be interested in the lift coefficient or the drag coefficient. And it's really useful to set up this specific quantity as a monitor. And the reason for doing that is that if you can set up the quantity that you're interested in as a monitor, you can monitor it specifically and check that it's converging. And the reason for doing this is, from personal experience, and some of you may have found this as well, is that some quantities in the domain converge faster than others. So in the same way that when we looked at those point monitors for velocity, the velocity quite near the inlet often converges a lot quicker than the velocity near the outlet, we find the same thing for forces on surfaces, and for example monitors in the wake of an object. We often find that the lift coefficient, for example, converges very quickly, whereas the wake behind the airfoil takes a lot longer to converge. And this is quite useful because often you don't know at what point you should stop and turn off your CFD solution and say, I'm finished, everything that I'm interested in has converged, because different components of that solution converge at different rates. Now, the final thing I wanted to talk about, I don't want to go into this in too much detail because, of course, every CFD case is different and there's a limited amount of help and scope that I can give in one presentation talk. But in CFD, one of the things that people often struggle with the most is convergence difficulties, or their case is broken or doesn't work for some reason. Maybe it diverges instantly, or maybe it comes up with some kind of error message that won't let it run. And what I wanted to do is just quickly mention some common areas that cause difficulties converging a CFD case. And these are kind of obvious things to check in your CFD case if you have difficulties. These are probably the first things you should think about and look about, which might help improve it in future. And when you have convergence difficulties, these are all going to be reflected in the various monitors that we've set up. So you'll see this in the residuals. The residuals may be flat or oscillate, or they may increase. You'll see this in the global imbalance. You may have imbalances of 100% or more. And in your monitors as well, as you set them up, you find the temperatures may be beyond the maximum and minimum limits, for example. And some of the reasons that you can get these difficulties with CFD solutions is, the obvious one is poor mesh quality. If you have really skewed cells, or your non-orthogonality is greater than 90 degrees, for example, that's an easy one. If you have inverted cells, often if you have poorly specified boundary conditions, if your boundary conditions aren't set up sensibly, or if you've written your own user functionality to support your case and there's a bug or an error in that functionality, that can often lead to difficulties. And the other one, of course, is unsteady flow features. And this requires you to think a little bit about the physics of your problem and what your solution field is going to be looking like. If you have a region that's highly unsteady, for example, in that backward-facing step flow that we looked at earlier, we know that right behind the step there's going to be a recirculating region generating a lot of turbulence and unsteadiness. And if we try and solve that with a basic steady-state solver, we may find that the solution struggles to converge or may not converge at all. So also have a think about the physical flow features that might be trying to develop in your CFD solution and where they are. So this is really a summary slide to talk about those convergence difficulties. And What I want you to take away from this talk is that the residuals, the imbalances, the point monitors, the integrals, all of these things provide information to us. You have to think of yourself like a bit of a detective, and you're using all of the bits of evidence that you have to try and work out a picture and try and understand what's going on with your particular case. And also never forget that you can open up your solution in the post-processor itself and just directly look at what's happening. So you can always stop the solution, plot it in your in ParaView or TechPlot, for example, or Field View, and look at the velocity field and look at the temperatures. Is anything too high? Is anything too low? Can you see any unsteadiness? Are there any strange flow features? Maybe you have flow going into a wall or coming out somewhere which you didn't expect. And where do you think the error might be arising from? What do you think might be causing difficulty? Now, of course, I can't diagnose all convergence difficulties in one video, but I hope these has given you some things to think about when you're looking at and assessing your own CFD case, and you can try and work things out for yourself a bit like a detective. So just to summarize this lecture and really this whole series of lectures, the main takeaway point is that when you're assessing the convergence of your CFD, it's important to look at as many different metrics as you can all together. So residuals, global imbalances, point monitors, maximum and minimum field values, looking at all of these together, actually looking at the flow field, looking at the contour plots and interrogating, and can you see, are there any vectors going the wrong way, for example, or have you got any spurious values that are far too high? And the reason it's important to look at the different metrics together is because some of them, like residuals, are difficult to interpret, but the important thing is that different aspects of the CFD code converge at different rates. That's the main thing. So to think about this conceptually, you don't have one block solution that converges all at the same rate. You have different parts of the solution which converge at different rates. And it's important that you can check that all of the metrics that you care about are sufficiently converged when you choose to stop. And the main takeaway point, as always, is the more metrics you set up, the better. If you throw in an extra 5 point monitors for velocity and you don't end up using them, it doesn't matter, because really the space taken up by point monitors when they write data out is usually very small. So to put in as many metrics as you can. It probably takes an extra 20 minutes, half an hour to set up a load of extra metrics in your CFD case, but it's really worth doing, because the more you have, the more evidence you have when you're checking your CFD case while it's solving. So that wraps up my 4-part lecture series on residuals in CFD. We've covered a lot of information and we've gone into real detail explaining what residuals actually are, what the differences are between scaling, normalization, how the mass continuity error is treated differently. And I've also gone through a variety of different techniques which you can use to when assessing the overall convergence of your CFD case using point monitors, imbalances and residuals. So let me know in the comments section, have you found this set of talks helpful? Has it been useful for your understanding? Have you been able to get some new confidence when approaching your CFD cases and setting them up to assess convergence? Let me know in the comments section below. I'm really hoping that this set of talks has been extremely helpful for a lot of people, because I know that looking at residual plots and assessing convergence is often something that many of us struggle with, and is something we have to carry out on a day-to-day basis when using CFD codes. So let me know in the comments section. I look forward to hearing from you, and I'll see you in the next video.